Alright, so in the last video we went over the digamma function and its properties, and in the video before that we went over the digamma function's definition in terms of a sum, okay, and also in terms of the gamma function itself. Now I want to solve an integral using all of that. An integral is just going to be this one. It's very basic. It's going to be the integral from 0 to infinity e to the negative t log t dt. And in fact, this integral has a more interesting form, and that is the integral from 0 to 1 of log of 1 over t dt. And it's pretty easy to see why this is connected to that. Here, if you just make a substitution u equal to log of 1 over t, or in other words, negative log t, then I'll just show you this. When you take the derivative or take the differential on both sides, on the right hand side you get the negative sign, it's going to stay. The derivative of log t is just going to be 1 over t, and then by chain rule you multiply by a dt. Okay, but t, what is t in terms of u, right? Well, t right here, if we go ahead and negate both sides, so you get negative u equals 2, and then we exponentiate both sides, so e to the negative u is equal to, well, on the right hand side you're going to just be left with a t. So right here, this bottom is just e to the negative u. If you multiply this on both sides, you get, well, e to the negative u du is equal to negative dt. And this negative you can also move over here. So, yeah, let's go ahead and write this through. From here, we're going to have, all right, let's deal with the bounds in a second. This remaining part is going to be a logarithm, and then this inner logarithm we set to be equal to u. Okay, and then dt, well, is just negative, which I'm going to drag to the outside, e to the negative u du. All right, so that's the integral done. Now we just need to figure out the bounds. Well, when t equals 0, here see that when t equals 0, log of 0, as you approach it from the right hand side, it's going to spike down to negative infinity. So u is equal to negative of negative infinity or positive infinity. And when we plug 1 in, it's more simple. Log 1 is 0, negative 0 is 0, upper bound 0. So basically you use this negative sign right here to reverse the bound. So instead of going from 0 to infinity, you go, instead of going from infinity to 0, which is kind of weird, you go from 0 to infinity. So yeah, this integral is exactly equivalent to that. But how do we solve this guy, right? Okay, and for this, we're going to have to observe the gamma function. What happens when you take its derivative? The gamma function of, say, argument x, we're going to use x for once instead of z. I'm tired of writing that letter. We're going to have the integral from 0 to infinity, and then t to the x minus 1 e to the negative t dt. Well, if you take the derivative on both sides, the left-hand side you're going to get gamma prime of x. And on the right-hand side, well, you're going to have the derivative with respect to x. But according to Leibniz, you are able to interchange the order of integration and differentiation. So I'm going to put the integral on the outside. But that's only if you make the derivative a partial derivative, which I'm going to notate as that because I'm lazy. T to the x minus 1, e to the negative t dt. This one, e to the negative t, that's just a constant in terms of x. So we're going to bring that to the outside. Yes, okay. So e to the negative t. Okay, so now that's gone. How about this partial derivative of t to the x minus 1 with respect to x? Well, t is a constant in the x world. So say we have 2 to the x minus 1. Well, when we're trying to differentiate this, well, the 2 to the x minus 1 is going to repeat, and then we're going to have the natural logarithm of 2 multiplied on the side, and then of course chain rule, right? But the derivative of x minus 1 is just 1, so that's it. So analogously, right here, what we do is this t to the x minus 1 is going to repeat. And then we're going to have to multiply by the logarithm of the base, which is t. And then chain rule, but of course, same deal as earlier, it's just going to be 1. Okay, so just like that, by taking the derivative, we introduced a logarithm into our integrand. Now, we just have to find a value for x to get this term to go to 1. Because notice, if that goes to 1, then we have the exact integral that we were trying to solve, okay? And how do we do that? Well, we make the power 0. And to do that, we just set x equal to 1. So gamma prime of 1, well, it's going to 0 out to the power here, which is going to make this factor 1. So this is just equal to the integral from 0 to infinity of e to the negative t log t dt. Okay, nice. So we just figured this relation out. But gamma prime, we haven't really worked with that function yet. How are we supposed to figure this out? Well, we do know something that involves the gamma prime, right? And that is the logarithmic derivative of the gamma function is just gamma prime over gamma, but it's also the digamma function. So now we're on to basically the second major phase. Recall the definition of the digamma function, gamma prime over gamma. And, well, here we have a gamma prime of 1, so let's just set z equal to 1. And when we do that, gamma of 1 is pretty trivially going to go to 1. So if this bottom goes to 1, then we're just left with gamma prime of 1 on top. Well, we're just left with digamma, of 1 on the right-hand side. And, well, what is digamma of 1? Let's go ahead and recall its sum definition. So digamma of z, its definition is the negative Euler-Mascheroni constant, okay, plus the summation running over n is greater than or equal to 0, 1 over n plus 1 minus 1 over n plus z. And this is very easy to do because once you plug in z equals 1, so once you plug in digamma of 1, the sum you see collapses completely down to 0 because the inside becomes 0, and when you sum over 0, you just get 0. All you're left with is this negative gamma right here, or negative Euler-Mascheroni constant. Okay, so there we go. We have now just found, because digamma of 1 is equal to negative Euler-Mascheroni constant, then the gamma prime of 1 is also equal to the Euler-Mascheroni constant, but negative. And therefore, this integral right here, by way of the derivative of the gamma function, is just the negative Euler-Mascheroni constant. So that was very simple, but this is very important in a lot of places, especially because A, this inside has no elementary antiderivative, and B, well, it's very common to find something like integral of e to the negative t, where or times t maybe, where the two arguments where t is 2 layers apart. This is inside of a logarithm, and this is on top of an exponential. And because of that, they're kind of isolated from each other through 2 exponentials. This is just an inverse exponential, right? The logarithm. So, yeah, it's very common to find something like that where there's no elementary antiderivative, but we can use this if the bounds suffice. So that's why that is important, and I mean, that's pretty cool.